In this video, we're going to talk more about Fourier series. And I first introduced the big picture back in my previous video on this topic, and the link to that is down in the description. The idea was if I start with some function, like maybe this discontinuous function, this square wave that's 1 and then minus 1, I can try and approximate that function with a sum of trigonometric terms, a sum of sine terms and cosine terms. And as you can see here, this was the graph of the first 19 terms in some so-called Fourier series. It gives a pretty decent approximation, even with this crazy discontinuity that happens at the value of pi. Now, in this video, I want to answer a couple important questions. And the first of them is, well, how do I compute out what the coefficients in this Fourier series is? How do I figure out what the a0, the an, and the bn is? And then secondly, we're going to answer the question, well, when does a Fourier series actually converge and become a good approximation? So we're going to talk about both of those issues in this video. Now, first up, I'm actually going to begin with just a kind of random seeming integral, the integral of sine of m times t multiplied by sine of n times t. And this is just going to be an integral that's going to be very useful to us. So how do I evaluate it? Well, it turns out it depends on the values of the m and the n. If m is equal to n, then this is sine squared of m of t, and you can use a little trig identity, and I'll let you do it. It computes out and adds up to pi. If, however, the m and the n are different, if you try to evaluate this using, say, integration by parts, again, I'll let you do the grunt work of it, it actually is always 0 if m and n is different. And the way I sort of think about this is that if you imagine sine but with different frequencies, the multiplication with different frequencies always exactly cancels out. It always multiplies out to something that integrates to 0. So this is one of the most important little trig identities that's relevant for Fourier series. And there's a couple of them, because the same is true for cosine. Multiplication of cosine with different frequencies integrates out to 0. And if it's the same frequency, it integrates to pi. And finally, the last one I might want to consider is, what if I combine these two? Coses times sines. And this one doesn't matter about the m and the n. This one's always 0. Okay, so 3 different integrals, back to our original problem. We're going to use these in a moment. So where were we? We were trying to make the claim that we had a Fourier expansion that our f of t was going to be in some sense equal to this Fourier series. How do I find out what the a0, the an, and the bn are? Well, the first thing I'm going to do is I'm going to multiply both sides of this equation by sine of mt, and then I'm going to integrate from 0 to 2 pi. I'm always allowed to do the same thing to both sides of an equation. I can multiply by some other function and I can integrate it over some region. I can do that. If its original is equality, then I get equality here too. Now, let's think about what's going to happen. The first thing I'm going to note here is that the contribution from the a0 part is going to be just nothing. The reason here is that this a0 is multiplied by sine, and when you integrate sine over its period, you always get 0. Integration of constant times sine over its period is again going to be equal to 0. Then I can look at all the cosine terms, and all of those are going to be 0 by that previous identity. The integral of a cosine times a sine is always 0. Okay, finally I have a sum of sine terms, but notice here, the sum of sine terms is a whole bunch of sines of many different frequencies multiplied to just sine of mt, m sort of a specific value. Well, almost all of those are 0, again by my previous result. The only non-zero one is the specific case when n is equal to m, in which case I have bm sine of mt times sine of mt. And again, we had that integral on the previous page. If it was the same frequency, sine of mt times sine of mt, that integrated out to pi. Have the extra bm coming out and you get bm times pi. Okay, so in other words, I can clean this up a little bit here. And what I get is that bm is 1 over pi, the integral from 0 to pi of your function f of t times sine of mt dt. And this tells you something. Now I know how to figure out all of the coefficients of the form bm. They're just those specific integrals with whatever function f of t I have. Okay, great, we've solved that part of it. Let's continue. Instead, now what we're going to do is we're going to multiply by cosine on both sides and integrate from 0 to 2 pi. Similar kind of argument, the a0 over 2 term, that's going to cancel away when you integrate because integrating cosine over its period is just 0. Likewise, all the sine terms are going to go away because integrating sines times cosines always equals 0. What I'm left with then is the cosine times cosine terms, and most of those are 0, but there is one non-zero one, the time when m is equal to n, and I get the integral of am cos of mt times cos of mt, or cos of mt squared, which we evaluated out to be am times pi. And so again, I have a formula now for my cosine terms. There we have it, 1 over pi, the integral from 0 to 2 pi of f of t cosine of mt dt. So this means that for any specific value, I can get the am, I can get the bm. Only thing I don't have yet is that a naught out the front. To do that, well, same trick. I'm going to multiply both sides, but I'm just going to multiply by 1, and then I'm going to integrate from 0 to 2 pi. And now that I'm integrating by 1, all of the cosine terms go away, all of the sine terms go away. Here I'm integrating over their period, so they all go away. Only thing that remains is the a naught divided by 2. And that's easy enough to do. A naught divided by 2 times 2 pi. The 2's cancel. I get a naught times pi. And if I bring this one up, I'm going to get that a naught is 1 over pi, the integral from 0 to 2 pi of f of t times 1 dt. And if I have all three of my formulas here, that is my answer to how I find my coefficients. You'll note this is why I choose to canonically reference it as a naught divided by 2. It's because those 2's are going to cancel and mean that our formulas are all consistently 1 over pi. That's why it's defined that way. Okay, so those are our formulas, but let's go and apply it in a specific example. I'm going to talk about this specific function. It's 1 from 0 to pi, and then 0 from pi up to 2 pi. So 1 and then 0. So what I'm trying to do is figure out all of these different coefficients. I'm going to try to figure out the a naught, the am, and the bm. And so what do I do? Well, two things. If I plug in the f of t, the portions where the f of t are 1 means I'm just going to plug in 1. And then for the portions of f of t that are 0, that's between pi and 2 over pi, well, the easiest way to deal with this is just to change the endpoints of your integration. Because it's 0 from pi to 2 pi, instead of integrating all the way from 0 to 2 pi, I'm just going to integrate from 0 to pi in each place. So this is a little trick that I can use for this sort of discontinuous function. I'll integrate from 0 to pi, and then I'll just put the function 1 in. And then beyond that, it's 0, but you don't have to worry about that. Okay, so I have three different integrals. The first of them is easy to do. This is just going to be 1. Pi times 1 over pi is 1. For the second integral, again, I can do this. This is going to be a sine. There's a 1 over m that comes out. But you know what? Sine of any integer times pi is always 0. Sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, and sine of 0 is 0. So everything here is 0. Everything for the AMs is just 0. Okay, what about for the BMs? Well, if I do the same thing, the integral of sine is going to give a negative cosine of mt divided by m. And now it's not quite so easy. It's not the case that everything just cancels when I try to plug in the value of pi. So let's focus specifically on that. I'll clean up and give myself a little bit of space. If I plug in the value of pi, then what I'm going to get is this constant at the front, 1 over pi times minus 1 over m, just a coefficient at the front. Then, plugging in pi gives me cos of m pi minus 1, which is when you plug in 0. So how do I evaluate this? Now, it's actually a little bit of a trick here for dealing with these cosine terms, and I'm actually going to put up the plot of cosine just to help me with this. So what I'm trying to do here is like cosine of 1 pi, 2 pi, 3 pi, 4 pi, and so on. But exactly the values change. So for example, if m is an even number, right? M is 0 pi, 2 pi, 4 pi, 6 pi, etc. Then it's always the peak of my cosine. In other words, it's equal to 1. But if m is an odd integer, like 1, 3, 5, and so forth, this is like cosine of pi, cosine of 3 pi, and so forth, that's always minus 1. So it depends on whether m is even or odd. There's a sort of a parity issue appearing here. And so the way I can represent this thing that's either plus 1 or minus 1 is with an exponent. I replace cosine of m pi with minus 1 to the m. Let's check this makes sense. If I do say m equal to 2, that'd be minus 1 squared. Minus 1 squared would be 1. That's what I want. If m is equal to 1, then minus 1 to the 1 is negative 1. That's what I want. So this is how I can take my cosine of an integer number of values of pi and replace it with a minus 1 to the m. Okay, let me clean everything up one more time because I have one more step here. And I want to think about, well, what is minus 1 to the m minus 1? Depends on the value of m. If it's an even number, this would be 1 minus 1 is equal to 0. So anytime m is even, 1 minus 1 would be 0. But if m is odd, it'd be minus 1 minus 1. That would add up to a minus 2. There's another minus on the outside, so that would add up to plus 2. It's 2 divided by pi times m. That is my coefficient bm. So then if I want to take it and plug it into the general Fourier series, well, the a naught is 1. All of the a(n) terms are all going to be 0. I can get rid of all of those, and then I can write down the sine terms that are going to remain, and this is what I get. 1/2 plus the sum, and this is how I try to write only the odd terms. I write n equal to 1, 3, 5, dot, 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 just to indicate that I'm talking about odd terms only, up to infinity. Then it's the terms, the bm's that remain, 2 over pi times n sine of nt. That is my Fourier series for this specific function. Okay, so what we've answered is how you find a Fourier series. If you're given a function, you do those intervals, that tells you your coefficients, plug it into the formula. But it doesn't answer the question of whether that Fourier series actually converges to something that you care about. So I now present to you the Fourier convergence theorem. This theorem is the Fourier convergence theorem. And it gives an assumption if your f and your f prime are piecewise continuous on some interval minus L up to L. You could then imagine taking that function and periodically extending it beyond this interval, but for now it's just defined on this interval. Well then, the conclusion that this converges to precisely the f of t anywhere for any t value where the f of t is continuous. And that is, it's just a good approximation. Alternatively, if there's a discontinuity, then what it converges to is it converges to the midpoint of that discontinuity, halfway in between the top value and the bottom value. That's where this Fourier series is going to converge. So this is really nice because these are pretty relaxed conditions, f and f prime only being piecewise continuous. We're not demanding a lot. And what we get is this convergence series. It converges to the actual functions when it's continuous and to these midpoints when it doesn't. And then I've put down the general formulas for computing the a naught, the am, and the bm. So just to illustrate this final point, I can go all the way back to my original picture here, which is my discontinuous function. This is the one that went between 1 and minus 1, very slightly different than the example we did, which was 1 and 0, but nevertheless the same idea. And what we have here is that there's a convergence to the midpoint between the discontinuity. That's what we just expected to see from our theorem. But then away from the discontinuity at something like, for example, pi, we have a very, very good approximation. And if we took more terms than the 19 I told the computer to plot when they came up with this plot, if we took the limit as the number of terms went to infinity, it would indeed converge precisely. So that is the idea of Fourier series.